Hello everyone, and welcome back to Complex Differential Geometry. We're on the last lecture before Kähler manifolds, which is going to be lecture 11, so this is lecture 10. And we're going to be introducing metrics, which is going to be an important concept in defining Kähler manifolds. And it'll give us a chance to talk about the interesting um, structure that you get when you define metrics on complex vector bundles. So before we get started, let me do a brief recap. Last time in lecture 9, we talked about connections. A connection was this map, gamma E times omega 1 m. We defined the covariant derivative, which ate that omega 1 m using a vector field, and we denoted nabla x, and this was a map gamma E to gamma E. And then number 3, we looked at some properties. Not going to go over that. Basically, it was to say that, yes, it does indeed act like a directional derivative. Then we looked at the connection form omega. So in order to do that, we had to look at local frame fields. So basically, this was like nabla of E alpha is equal to omega alpha beta tensor E beta. Number 4, so we use that to define the curvature form. We went from talking about f nabla, which was defined as a tensor, and then we went to omega. But I later found out that they're actually the same thing. I mean, you can call it f nabla or you can call it omega. They're the same. So we'll call it f nabla from now on. And this was a 2 form. It was an endomorphism valued 2 form. And it's equal to d omega minus omega wedge omega. So then we looked at connections on complex vector bundles, connections on complex VBs, which ended up with this idea that nabla of J of S is equal to J of nabla of S. That was the complex compatibility condition. And then we also introduced the holomorphic structure. And on the vector bundle, which introduced this operator, the canonical Dolbeault operator. And we said that, okay, well, partial bar E of S has to equal 0. And, well, this would give us a holomorphic local section. And we use that idea to define a new kind of connection. Sorry, why am I writing 2? 7. I swear I can count. Holomorphics. So with the holomorphic structure, we then defined a holomorphic connection. So we split nabla into nabla 1 0 and nabla 0 1, and we said nabla 0 1 has to equal to the canonical Dolbeault operator. And so right, so the significance of this, I forgot to mention, is that this looks like the CR equations, and it's a generalization of the CR equations. Like if you look at something like let me write it like this: ds dz bar equals 0 for s being a function, right? So this is similar to this, right? So this is basically generalizing that condition, and whenever you want to prove that something is holomorphic, you inevitably come back to the CR equations. So that's what we did. And then lastly, we looked at the churn classes. So we looked at churn classes, and specifically, we looked at the first churn class and some of its properties. So that was it for lecture 9. So this was both part 1 and part 2. We covered quite a bit of stuff. So now we're ready to get into metrics, and we're going to start off in the real space again. This is kind of a theme. We're going to start in the real space, and then we're going to extend it to the complex space. So we'll see if we can finish all of this in one session this time. It is 10-ish pages, and last time lecture 9 was 10-ish pages, and it took two sessions. So we'll see how it goes. Okay, so the first thing that we're going to define is a Riemannian metric. So Riemannian metric is a 0-2 tensor field. So again, as I remind every time, tensor field means that we're assuming that it's smooth. That's the way we're using the word tensor field. And so it has the following properties. One, we call it G, forgot to mention that. So it has property number 1 is that it's positive definite. Positive definite. This means that GP of, so right, well, what we're doing here is that we're going to define it pointwise. So we're thinking of G restricted to P, which we're going to call GP, right? So GP is the tensor that is assigned by the smooth tensor field at the point P. So GP of XP YP is not equal to 0 for some YP, right? Element of TPM. So basically what it's saying is that if you take any X, if you take any XP, there has to be at least one YP for which this is not equal to 0. And number 2 is the symmetry property, symmetry, which says that GXP YP is equal to, or GP of YP XP for all XP YP element of TPM. So if we have a Riemannian metric on the manifold, so if the manifold admits a Riemannian metric, then it's called a Riemannian manifold. Pretty self-explanatory. Riemannian manifold is a pair M and G. So it's a choice of Riemannian manifold. It's a choice of Riemannian metric on the manifold. So this is a little bit of fluff that I'm going to talk about right now. It's not necessary for the overall picture, but since we talked so much about how we would need metric spaces in order to define lengths and angles and such things, I wanted to talk a little bit about how the metric is used to define lengths and angles really quickly. So when you have a metric, you can define something called an inner product on vectors. So the way you define it is like this: GP of, it's defined pointwise on each of the tangent spaces. So you get this, and we basically just use that as our inner product. So any if you're thinking of an inner product of vectors in a vector space, then any 0-2 tensor will work as an inner product, and this is going to be an important idea going forward, especially when we go to Hermitian metrics. So firstly, let's define length. Length is, if I can spell length correctly, so length is this function. It's double bar, something in the middle of a vector xp, which is we tend to write this as like that. It's also called the norm, and we basically define it as the square root of gp of xp twice. And you'll probably like see the resemblance with like the Euclidean metric, which is kind of hidden inside the Pythagoras theorem. So where there's like a square root of things being multiplied with each other as well. So this is how in general we define something called length. And so then how do we define angles? Well, okay, angles. Let's call this function theta. So theta of, let's say we want to measure the angle between two different vectors, xp and yp. Then this is equal to the arc cosine. Some people call this the inverse cosine of gp of xp yp divided by, well, now we have the length, so we can safely use this notation. And because of the Cauchy-Schwarz inequality, this is definitely between -1 and 1. So this arc cosine is well defined, and so we're just using if you're wondering where the arc cosine is coming from because we're on the manifold, since this is going to be a real number, this is an element of R. So we're just using the arc cosine that's defined in the real space. So we don't need to do anything fancy to define like series and have like some sort of definition of arc cosine on the manifold. We're just using the plain old arc cosine. So that's how you get angles. And this kind of illustrates why you need a metric in order to, or like what a metric has to do with measuring lengths and angles. It literally is the thing that you use to define what a length or an angle is. And then in R3, with the Euclidean metric, this will become square root of x dot x, right? And this looks exactly like the formula that you use for calculating angles too, which is x dot x over the length of sorry, it should be x dot y, right? X dot y divided by the length of x and then the length of y. So, and then of course you have to take the arc cosine of that. So that's how we measure lengths and angles. So there's also the concept of distance, which I'm going to define. This is also not very necessary, so we're just going to very quickly define it. Distance on M. The way we define it is that we define something called a distance function between 2 points P and Q, and it's going to be the infimum. This is all going to be very intuitive in a second. L of gamma, where gamma is a parametric curve, 0 to 1, such that uh, gamma of 0 is equal to p and gamma of 1 is equal to q, which means that the start of the path is p and then the end of the path is q. And why are we taking the infimum here? Well, L of gamma is a function that we're about to define, and this is where the metric comes in. So L of gamma is equal to the integral from 0 to 1 of the length of gamma prime of t dt. And remember from lecture 1 that these parametric curves have a derivative associated with them. So gamma of t has this equivalence class, and that equivalence class is related to a vector, which is a tangent vector. And tangent vectors are essentially modeling velocity vectors. So this is the tangent or the velocity of the curve at every point. So this gives you the length of the curve. So this is the length of the curve, length of curve. And when we take the infimum, what we're saying is, well, this is the set of all curves from P to Q. Take the shortest distance. The curve with the shortest length is the distance between the 2 points. That seems pretty intuitive, right? So that's how we define distance on the manifold. The interesting thing and the real reason I wanted to define this is because dpq satisfies the axioms of the uh, distance function. I don't want to also call it the metric because we're going to get confused with the metric that is g. I'll call it the distance function of a metric space. And so that makes any Riemannian manifold, because we can always do this as long as we have this whole business going on. So the metric is hidden in this norm, right? So this requires the metric. So as long as we have the metric, we can define this distance function. So any Riemannian manifold is a metric space. So I mean, you can verify. The main thing that you have to verify is that if you have dxz, then that is greater than or equal to dxy plus dyz. This is called the triangle inequality. Okay, so there's an interesting connection that you can define on uh, on a Riemannian manifold. Levi-Civita. I'm dropping letters all the time. Levi-Civita connection. There's a very important sounding theorem because the theorem is called, this is what it's written in all of the books. It's the fundamental theorem of Riemannian geometry. Really important, apparently, that you have to know that every Riemannian manifold admits a unique connection that has two properties. One, it's torsion free. So here's where that torsion freeness is kind of coming into play, right? That's why we set it up in the last lecture. So txy is equal to 0. And t obviously is defined using the connection. And then 2, it's metric compatible. We talk a lot about compatibility in differential geometry. In this case, metric compatibility amounts to the idea that the covariant derivative of G is equal to 0, and where this is going to be the Levi-Civita connection. This also can be translated into the following condition. Let me write it out. X g of yz is equal to g of nabla x y z plus g of y nabla x z. Yeah, so these are equivalent to each other. So the point being that every Riemannian manifold has a Levi-Civita connection, and this is a unique connection that has that is torsion free, and it commutes uh, with the metric, and therefore, mm, right, it gives us a canonical way. It gives us a canonical or a preferred way to differentiate vector fields on an affinely connected manifold. Affinely connected manifold. Obviously, the connection has to be on the tangent space, or else all of the tensors that we're defining are not going to be connected to each other. Because we're specifically looking at tensors that are defined over the tangent bundle. So right, and in local coordinates, the Levi-Civita connection ends up having, let's say, coordinates or coefficients that look like this. We're going to need to define a few things here. So we got partial I, G, J, L plus partial J, G, I, L minus partial L, G, I, J. So I haven't actually defined what these things are, G, G, J, L. So these, the way you would get these is you take, I have a section that I rewrote into lecture 4 after the fact about how you figure out the basis decomposition for a tensor. So we'll look at that a little bit right now. So if you have something like this where you input two basis vector fields, then the number that you get from here is called GJK, and this is called the component of G. And that's what we're doing here. And if you put this into a matrix, then you get the matrix GJK. I'm going to write it like this so that we can separate it from the tensor. But if you take the inverse of this matrix, then you get this matrix GJK. So this is these are the components of the inverse of the metric. Inverse. Anyway, this is a pretty famous formula, so I wanted to include it. And so the main thing to remember is that this is not a tensor. Not a tensor. And this has exactly to do with the fact that omega, the connection form that we looked at, omega alpha beta was also not a tensor. Right? So since omega, since these two are actually related to each other, I don't have on me exactly what the relationship is, but I might put a little insert here to write out the actual formula. But these are actually related to each other, and And the fact that this is not a tensor is also the reason why this is not a tensor. It's because their transformation properties don't line up in that way. Hello, this is editing Saif. This is the insert for why omega and the Christoffel symbols are related, and we'll talk a little bit about why the Christoffel symbols are not tensors from one point of view. So let's start by picking a point P element of M, which associates us with a tangent space TPM, and we choose a coordinate basis on it, which, if you remember from lecture 1, the coordinate basis on the tangent space is a bunch of partial derivatives. These are from the local coordinates that we assign on the specific local patch of the manifold, right? So these are local coordinates. So the way we start with this is that we use the definition of the connection form in terms of the connection. So we say that nabla of EJ is equal to the connection form WKJ tensored with the appropriate basis vector. And this is a form that is this is an object of the type omega 1 m tensor gamma e, where this is the gamma e portion and this is the omega 1 m portion. But if we use the coordinate basis, what does this tell us? Then we get partial xj is equal to omega kj tensored partial xk, right? We just substituted the coordinate basis, nothing complicated here. So then we can also expand out. So now what we're going to do is we're going to coordinate decompose the omega 1 m portion of this definition. So this is also equal to, if we look at it like this, we can say that if we remember what the definition of the coordinate covariant derivative is, it was something like this: nabla x of s is equal to nabla of s all applied on x. Remember, this gives us an omega 1 m cross gamma e, right? And so applying it on a vector field will give us a number. So that, or it will give us the remaining vector field, right? It will eat this one form, and it will keep this vector field. Right, so first of all, let's coordinate decompose. So partial xj. This is something of this type, right? So we're going to coordinate decompose this one form. Then what do we get? We get gamma of partial xj. I'm going to write it in one way and then we're going to rewrite it. We're going to say ei tensor dx, or sorry, epsilon I. So this is a coordinate decomposition. How do we know this? This is our basis covector, and this is the component that we would get for that basis covector. This is the connection form applied on, yeah, this is the form of the connection, this connection form that is applied on the EI basis vector. So let's substitute these. These are actually partial xi, and this is dxi, right? So if we evaluate this using this definition, then what we get is nabla of partial xi of partial xj. But this is just equal to the Christoffel symbol. This is by definition. We just defined it. You can scroll back to the part of the video where we define this. This is equal to gamma kij. This is the Christoffel symbol kij multiplied by partial partial xk. Remember, this is a vector field valued or section of E valued, not necessarily a vector field, but a section of E valued object, and that's why its basis is uh, in terms of the coordinate basis of the vector field. So if we put this all together, then we get that nabla of partial partial xj is equal to gamma of kij partial partial xk tensor dxi. Now, we have a partial partial xk here and a partial partial xk here. So if we just take that, and let's say we compare the other values here, then we get that, let me use a different color here, then this part has to be equal to the rest of this, right? So therefore, omega kij or kj is equal to the Christoffel symbol kij tensored dxi. And so that is the relationship between the two. So they're directly connected to each other. And if we look at the properties of the transformation properties of the connection form, remember that they look like this. Omega prime is equal to, or the way we were doing it, omega on S prime is equal to dA dot A inverse plus A into omega in the S frame into A inverse, where S prime is equal to A dot S. These were two local frame fields. Okay, so so this was the transformation matrix, and this is the part, this, well, specifically this part, makes it not tensorial. So we know that the connection form is not tensorial. So then, and we know that it's a matrix valued form and all this, all that complicated business, right? But that means that since this part is tensorial, right? dxi is tensorial. That means that these connection coefficients, or the Christoffel symbols, these are not tensorial. They have to be, so that the left-hand side of the equation can be not tensorial. So this is tensorial, right? So big takeaway, the Christoffel symbols are not tensorial. Okay, so back to the live recording. All right, so we're going to need to define some really important curvature tensors now, curvature tensors. So remember that we had F nabla last time we had the curvature form. So that was a 0-2 tensor. And now, given that we have the Levi-Civita connection and we have a Riemannian manifold, we can define a different type of curvature. So if I have, it's called the Riemann, those ends are not intelligible, Riemann curvature tensor. So the Riemann curvature tensor is a 1-3, it's a 1-3 tensor field. Okay, I should talk about something here. So it's called the Riemann curvature tensor, and I'm, by force of habit, I'm going to call it the Riemann curvature tensor. But it's a tensor field. It's not a tensor. It's a tensor once you restrict it to a specific point, but every like it doesn't even really make sense to talk about the curvature tensor at a single point, because you want to talk about curvature. You can talk about curvature around a point, but you can't really talk about curvature at a point. Points don't really have curvature. So the Riemann curvature tensor should really be called the Riemann curvature tensor field, and it's a 1-3 tensor field. And So it looks like this. This definition is not going to be very explanatory, but we're going to do something about that in a little bit. Nabla y, nabla x. You may be able to see the pattern here emerging, or you might be able to recognize this expression. So this is actually f nabla if we take f nabla to be on Tm, right? If we're specifically on the affine bundle, then this ends up being the same, and in fact, we can say Rxy is equal to f nabla xy, where the usual way that we talk about the Riemann curvature tensor is not as this um, 4-input tensor, but instead we think of it as this um, operator here, because we know that f nabla takes us from gamma e to gamma e, right? So that's what rxy does as well. So what we do is we kind of multiply it like a matrix, like that. And so we define this as being, yeah, so f nabla xy of z. So, and then we just omit the last input, and that instead of like every tensor returns a scalar, but if we remove the last kind of covector input, then we get uh, a vector field, right? So this is the usual format in which we see the Riemann tensor. And I wanted to speak a little bit on why the Riemann tensor is a 1-3 tensor field. It's because there are 4 things that you want to keep track of when you're talking about the curvature of a manifold. This is what is telling you the curvature of the manifold. So you need to keep track of, one, the input vector, because the way that the Riemann tensor is measuring curvature is that it's talking about a vector that's being moved around on a parallelogram, and then it's telling you how much the did the vector change after you moved it around the parallelogram, right? So I kind of think of tensors as each of the inputs of the tensors tells me that there's another direction involved. So there are 4 directions involved with the Riemann curvature tensor. One is the direction of the original vector, and or what component of the vector input vector you're looking at. The second is the direction of the parallelogram. So the parallelogram has 2 axes. One of them is this axis right here, and let me highlight that in a different color. One of them is this axis right here, and the other one is this axis. So that gives you 2 more directions. So you have 2 more degrees of freedom of which directions on the manifold you want the parallelogram to be pointing in. And then you have the component of the change, because the change is also a vector. It could change in any direction. So there are 4 directions associated with the curvature of a manifold, and the Riemann curvature tensor captures all of it. It captures all the curvature information on the tangent bundle. So now that's going to be contrasted with the next curvature that we're going to look at, which is called the Ricci curvature. So the Ricci curvature. And the Ricci curvature is actually a curvature that is derived from the Riemann curvature. I tried to define the Ricci curvature, or tried to look for a definition of the Ricci curvature that was coordinate independent, because that's like the modern formulation of differential geometry kind of prefers coordinate independent formulations. It's really hard, though, to define the Ricci curvature without coordinates, because this is the definition. This is the coordinate-free definition of the Ricci curvature. And I think you'll agree that it's very hard to understand what the heck is going on here. So when you're coordinate free, the trace operation is a little bit difficult to understand. This is telling you about a matrix. It's telling you about a matrix that takes you from X to Rxyz, right? It's not the trace of Rxy. It's the trace of whatever matrix will take you from X to Rxy of Z. And so um, it's because, like, in physics, we would usually define this by saying that the Ricci curvature R alpha beta is equal to the Riemann curvature, but with one of the inputs summed over itself, like that. The first and third inputs. But obviously, this is not a coordinate independent way to define it because these are the components of the tensor. They're not the tensor itself. So the way that you write this in coordinate free notation is like this, where this is telling you that we're taking the um, the trace over the first and the third inputs. So when you coordinatize it, this is essentially what you get. And the effect that the Ricci tensor has, or like the difference between the Ricci tensor and the Riemann tensor, is that the Ricci tensor is averaging. The trace is like an averaging operation. So the Ricci curvature averages the curvature in every direction. And so once you take the Ricci curvature of something, you forget which direction the curvature was in. You just get an average curvature for that specific parallelogram. So then you can do something else where you can take another. If this is your Ricci curvature, right? Then you can take G alpha beta, and you can trace over it again, and so that gives you something called the Ricci scalar. So Ricci scalar, and this is an even more averaged version of the curvature. This is telling you for like a small patch around your point, uh, what is like a number that is associated with that point that is telling you how curved it is in general. So um, so these are like progressively, like, the idea basically is that Riemann is like the highest in terms of detail, so highest, and then you lose detail as you keep going. So sometimes it's called the scalar curvature. So the scalar curvature is the lowest resolution form of the curvature. So these are going to be important. Like, the reason we're talking about the Riemann curvature and the Ricci curvature is because they're going to pop up when we talk about Calabi-Yau manifolds, because the Calabi-Yau manifolds are actually Ricci flat. And so that's going to become, these kinds of curvature are going to become important when we talk about them. Okay, so we're done with the real part of talking about metrics, and so now we're going to extend our metrics to the complex space, and this is going to become quite interesting because we're almost going to get out of talking about tensors, and then we're going to bring it back in a special way. So we're going to talk about complex extensions to the Riemann or the Riemannian metric. That I really feel like every time I write Riemannian, I have to do a double take and rewrite it so that people actually understand what I'm talking about. Riemannian metric. Okay. So the complex version of the Riemannian metric is called a Hermitian metric. And the differences between the Riemannian metric and the Hermitian metric come from basically the requirements of the complex space. one thing is that remember that we defined lengths, right? And there's not really a good geometric interpretation of a length if you don't if it's not a real number, right? So some of the things that we're going to define right now are going to be motivated by the fact that the norm should be real, and uh, and the angle between two vectors should be a real number, right? So this is going to affect the way that we so the Riemannian metric was a 0-2 tensor, right? So let's define a Hermitian metric and we'll see how it differs. So a Hermitian metric H is a map from uh, the smooth sections on E times the smooth sections on E to C, right? And you might say that, oh, why didn't we just call this a covector field? And that's because the second input is not linear. Okay, so um, first things first, uh, it's linear in its first input, linear in input 1. So that's what you expect. So we define it pointwise. So it's like A VP, or V1P is what I called it, A V1P plus B V2P. W is equal to HP, or A HP V1P WP plus B HP V2P WP, right? And it has this conjugate symmetry. This is the analog uh, of conjugate symmetry. This is the analog of the symmetry that the Riemannian metric had. So H of VW is equal to, or I wrote it like this, HP of VP WP is equal to HP of WP VP, but you have to take the complex conjugate of the whole thing. This, along, if we add this axiom to this axiom, or this property, then what we get is something called conjugate linearity. So HP of VP A W1P plus B W2P is equal to A bar, so the complex conjugate, HP VP W1P plus B HP VP W2P. So this disqualifies the Hermitian metric from being a tensor because it's linear in its first input and it's conjugate linear, or there's a special term for it. The Hermitian metric is called sesquilinear. And I wanted to just take a brief moment to talk about why it's called sesquilinear because I love the reasoning for it. So conjugate linearity, which this is called conjugate linearity, is a form of a general topic called, or a general kind of linearity called semilinearity, which you can kind of think of as half of a linearity, even though that isn't literally what it is. But if you think of it as half of a linearity, well, you have one input that is linear and one input that is half linear, and in fact, sesqui is a Latin prefix that means 1.5. So what it's really saying is that Hermitian metric is 1.5 linear, which doesn't make any literal sense, but I love that fact that that's how they named it. So so this is the Hermitian metric, instead of being a bilinear form, is called a sesquilinear form. So but there's an interesting way in which we can actually turn the Hermitian metric into a bona fide tensor. And it involves a clever trick in turning it from something that looks like this. So we have H, it goes from gamma E cross gamma E to the complex numbers, right? We're going to define a new object, H hat, um, that goes from gamma of E star. Uh, sorry, is that how I want to talk about it? I think we should say it like this. H is an element of gamma of E star times E bar star, where E bar is the dual bundle. Dual bundle. Which last time we talked about the dual bundle, as a small refresher, the dual bundle is the bundle where the fibers are the dual spaces of the regular bundle. So if E has EP, then E bar has EP star, right? Now my notation isn't very consistent here because I didn't expect there to have to talk about dual bundles. So there are a few places where I'm using bars and stars in an inconsistent way. I'll fix that up in the lecture notes, but this is essentially it. So um, yeah, so basically E bar P is this. So if we do this, what we can say is like so there's supposed to be a hat here. So the way we define this is like that, VP times, or V in this case, since we're talking about the tensor field. So we have V times W bar. W bar is an element of the dual bundle. And we say that this is equal to H of VW. And so what this has the effect of is that since we've conjugated this already, it reverses the conjugation that we would have to do um, when we normally apply the conjugate linearity. And so the two conjugates cancel out, and so we get linearity in the second slot as well. So this is a true bilinear form. So this is actually a 0-2 tensor, which is another way of saying bilinear form, or tensor field, in fact. Now, here I have to warn people about an abuse of notation that is very common in the literature, which is that people will essentially move between talking about H and talking about H hat, but they won't name them different things. They'll call H and H hat the same thing. They'll call them both H, and they'll contextually switch between talking about H and talking about H hat. And so if you see people defining the Hermitian metric as a bilinear form, then they're actually talking about H hat. And if we use the bilinear form, then we're also going to be talking about H hat as well. So, or like we're going to use the name H hat when we're referring to it. So that is the Hermitian metric. So we just talked about, so there's a very similar kind of coordinate decomposition. So the way we decompose this is we have that. I think it should be something like this. Yeah, EK bar. So then we get, yeah. So the way we denote that is EJ EK bar, and then we write, so this is a number, right? Because we are using up both of the slots of our bilinear form. So then we get something that looks like this. Right? Or we shouldn't have that part here, but yeah. So this is the component form of uh, our Hermitian metric. So this is all well and good, But what is interesting about the Hermitian metric is that it's actually hiding a Riemannian metric inside of it. So what we have is a Riemannian metric. I'm not going to spell out the whole thing. Riemannian metric with, or that is compatible with J, the complex structure. So we have one problem though. We want to induce this Riemannian metric from our Hermitian metric, but the Riemannian metric lives on Tm, and we are currently on T10m. This is where h of xy lives, and so g, this is where g of xy lives, right? If it exists, right? So we need to use this isomorphism, which says that we can map from x to half x minus j of x. So this format should be familiar. It's the same format that we used in lecture 3, where we decompose phi into phi 1 and phi 2, and that was very similarly, this was in V star out cross C, and these were the holomorphic and anti-holomorphic parts. And so what we're doing is we're mapping the entire vector, we're mapping phi to phi 1 in our case, right? So, and we'd have to show that this is an isomorphism. We're not going to do that, but what we are going to do is we're going to define g of xy as the real part of h of xy. And now, I mean, yeah, this is just a function. How do we know that this is a Riemannian metric? Well, we have to prove that it satisfies the properties of a Riemannian metric. So 1, it has to be positive definite. Positive definite. This is induced from the fact that the Hermitian metric is positive definite. It has to be non-degenerate. This is also induced from the fact that the Hermitian metric is non-degenerate. And number 3, it has to be symmetric. So let's prove that. Symmetric. G of xy is equal to the real part of h of xy, which is equal to the real part of, well, let's use the sesquilinearity of xy. So we can rewrite that as the conjugate of hyx. But since we're taking the real part of a complex number, the conjugation doesn't matter. So real part, this is the same thing as saying the real part of h of yx. And so, but this is just the definition of g of yx. And there we go. G of xy is equal to g of yx, which means it's symmetric. So this is a bona fide Riemannian metric. So now, what were we talking about with the compatibility concern, right? So let's show that G is indeed compatible. So number 1, what we did is we induced a Riemannian metric from H, right? So number 2, what we're going to do is we're going to show compatibility. Right? With J. So how do we do that? So first of all, we start with h of j of x, j of y, and then we say that, well, since x is an element of the holomorphic tangent bundle, then we know that j of x is equal to ix, which means that h of this, we can decompose this as h of ix, and same thing for y, so iy, and so we get so if we use this sesquilinearity, we get that this first I will turn out to be a plus I, and when we take out the second I, it'll turn into a minus I. So plus I minus I into h of xy, which is equal to, so obviously this is plus 1, so this is h of xy. So then what we've said is that h of j of x, j of y, is equal to h of xy. What happens if we take the real part of both sides? I'm going to give myself a little bit more space here. So then this just says that g of j of x, j of y, is equal to g of xy. Now, this is true all the time, right? This is true because the Hermitian metric always is sesquilinear. Not all Riemannian metrics, though, will satisfy this relationship. Only, I mean, or I don't want to say only, but one way to make it satisfy this relationship is to induce it from a Hermitian metric. So G is compatible with J. So they're commuting with each other, which means that if I use the complex structure on my vector fields and then apply G, it is the same as if I didn't apply G first, right? So that's why they're compatible. Now we've talked a lot about the real part of the Hermitian metric. So what about the imaginary part? Is the imaginary part important? And it turns out that the imaginary part is very important. Um, so we call it omega, omega of xy. And so we define this to be the imaginary part of h of xy. And this is also a two form. This, just like G and H, they're two forms. And so this two form is called the fundamental form. Fundamental form, or the more interesting name, it's called the Kähler form. Ooh, Kähler manifolds. So this has something to do with Kähler manifolds, as we'll see next time. But we would like to derive some results for this form. And the first thing that we'd like to say is that now we have a full decomposition of the Hermitian metric, which is equal to, in its real and imaginary parts. So we get that this is equal to this. So we're going to use this expansion to derive some of our future results. So moving on. So the first thing that we would like to do is we are going to take h of j of x, y, and we're going to use that same thing, jx is equal to ix, to decompose this. H of ix y is equal to I h of xy. And so now, if we take the decomposition that we just used into the real and imaginary parts, we get g of j of x y plus I omega j of x y. Then that's equal to I times g of xy plus I omega xy. And so what we end up with is, if we multiply out, then we get I of gxy minus omega xy. So here we can do this kind of okay, let me not get ahead of myself. Let's see comparing the real and imaginary parts, what do we get? We get omega xy is equal to minus g of j of x y, and we get that g of xy is equal to omega j x y. And here's where there's an interesting convention where sometimes we will define omega xy. Let me call it omega tilde just so that you're not confused. So we'll sometimes define it as this, the negative of the imaginary, because I think the main motivation is so that this one is positive and this one is negative. We want this relationship to be um, not have a sign between them. So we might go with omega tilde as our um, definition to make things more simple. But at the end of the day, it doesn't matter because in this decomposition, right? Because hxy is equal to gxy plus I omega xy, right? That's what we had currently. But if we substitute that with omega tilde, then we get minus omega tilde. So even if, so now what we're going to do is we're going to substitute this in, and no matter if we use the first convention or the second convention, we're still going to have a negative sign. So mainly the convention is just to make sure that this result that we got here, which is an important result, is positive. So no matter which way we slice it, we're going to get a minus sign here. So we're going to get minus g j of x y. And you can think of this as kind of a slanted complexification, which preserves the sesquilinearity of hxy, right? But you can think of it as a slanted complexification of the Riemannian metric of g, right? So that is kind of another way of thinking about the Hermitian metric, is that you can make it from a Riemannian metric on Tm. So we have one more result to look at. So we showed that g of xy is symmetric. We had to show it because we wanted it to be a Riemannian metric, and so it had to be symmetric. Well, let's see at what happens to omega xy. So omega xy is equal to g of j of x y, right? So let's see if we can't decompose this in a certain way. So obviously we will be able to, but we're going to use a specific result here. Let's start with the Hermitian metric again, use its sesquilinearity to flip the inputs, and then let's say that this implies that gxy minus I g j of x j of y, or j of xy, and this is equal to g of x g of yx minus or plus I am getting confused with the conjugation as well, plus I g of j of y x, right? From this flipped h, that's where we get that from, and this term from. So again, if we compare the real and complex parts, or the real and imaginary parts, the real part is self-explanatory, gxy is equal to gyx, but the imaginary part tells us that g of j of xy is equal to minus of g of j of y x. So that's how we will be able to flip the yeah, so what we were looking for was a rule that would allow us to flip the x and the y, and so that's what we got. So g of j of y x, sorry, there was supposed to be a minus sign here in the definition, or we could, if we were using the new definition, then there's a plus sign here. It doesn't actually matter because then it flips here, and then this is equal to minus omega y x, right? And so what we find, the interesting thing, is that omega xy is equal to minus omega yx, which means that the Kähler form is antisymmetric, which means it's an exterior form. And in fact, since it's a smooth form, so therefore it is an exterior differential 2 form. Omega is an exterior differential 2 form. And it's also non-degenerate, right? Now, this is a sneak peek for next time, but if such a 2 form that exists everywhere is non-degenerate, if it's closed, if d omega is equal to 0, we actually get something called a symplectic manifold, and that's the last structure that we're going to need in order to make our Hermitian manifold into a Kähler manifold. So that is why this is called the Kähler form, is because it allows us to make it into a Kähler manifold. There's a little bit of sneak peek. We're going to talk about it a lot more in the next lecture, but this is why this imaginary part is so important. And so our Kähler manifold is going to have 3 structures. It's going to have a Riemannian metric, so it's a Riemannian structure. It already has the complex structure J, and then it's going to have the symplectic structure, which is omega. So that is a little bit of a sneak peek of why the Kähler manifold is so elegant, is because it wraps these 3 structures together in a compatible combination. So we just talked about the compatibility between the Riemannian metric and the complex structure J, and we talked about the Kähler form. So now we're going to move on to talking about which this is the Kähler form. Kähler form. And so we're going to now move on to talking about Hermitian vector bundles. So we're going to talk about Hermitian vector bundles. So Hermitian vector bundles are pretty self-explanatory. If you have a vector bundle, E, and you are able to define this map, H hat, which is an element of gamma of E star times E bar star. That's how you pronounce that. Then, or equivalently, you can define H, which is the sesquilinear form. As we showed, their output is equal, so you can use either one of them, and the the resulting structure is the same. It's just that with with H hat, the advantage is that you can use tensor algebra with it, and which you can't do with H. You have to just kind of do things manually by looking at the function and all that kind of stuff, where you'll have to do some kind of functional analysis. I don't know if that's the right term for it, but with H hat, you'll be able to use all of the results of tensor analysis in order to make your manipulation easier. So these are equivalent, but basically a Hermitian vector bundle is a vector bundle that has a Hermitian metric attached to it. And this is one place where I think it's a good time to remind people that a Hermitian metric or a metric is something that you define firstly on each of the vector spaces, right? And then you smoothly take a section of those vector spaces to define the metric on the entire manifold. But the metric is not on the manifold. The metric is on the vector bundle, because it's a section of the vector bundle that actually has the metric on it. So the connection connects the vector bundle, and the metric is a measuring device on the vector bundle, because what does it do? It measures the vectors. It doesn't measure anything on the manifold itself. The only thing that we measured on the manifold was the distance between 2 points, but we measured the distance between 2 points by leveraging the fact that the manifold had a vector bundle on it. If the manifold didn't have a tangent bundle, we couldn't have done that. So one thing, the very important thing, the baseline or the summary of what I've just said is that keep in mind that metrics are things that are on vector bundles. And in this specific situation, we're thinking about the vector bundle being the tangent bundle. Now, Hermitian vector bundles can be like more general. That's why I'm using E and not TM. But um, our results are going to usually just use TM as the special case. So because we're going to be interested in affinely connected manifolds. Okay, PSA over. So yeah, I mean, a Hermitian manifold is the next thing we're going to define. Hermitian manifold. This is also very self-explanatory. I feel like whenever we define a manifold, we've already done all of the work. We're like, look at all this rich structure. Now, what if there was a manifold that had that structure? Call it the that manifold. So that's what we're doing here as well. So a Hermitian manifold is a manifold that has a Hermitian bundle over it. So, or equivalently, the way you could think about it, the way I wrote it in the notes is that a Hermitian manifold has a tangent. If it has a tangent space T10M, the holomorphic tangent space, then that holomorphic tangent space has a Hermitian metric on it. And having a Hermitian metric on a bundle is what makes it a Hermitian vector bundle. That's why I was saying that it has a Hermitian vector bundle. But specifically, it has a Hermitian vector bundle on its holomorphic tangent bundle, not its whole tangent bundle. So that's an important thing to note. This is actually equivalent to saying that it has a Riemannian metric that satisfies GJX, GJ, or JY equal to G of XY for all XY element of Tm. So these are equivalent ways of defining a Hermitian manifold. So our first proof for the lecture is going to be to prove that every complex manifold, so proposition, every complex, I said complex manifold, I meant complex vector bundle. Every complex vector bundle, I just talked about how metrics are defined on vector bundles, and then I said manifold. Every complex vector bundle admits a Hermitian metric. So this is a non-trivial statement. You might be wondering, well, we just said that we have Hermitian manifolds that have Hermitian metrics on them, right? But that's for a Hermitian manifold, right? That's for a manifold that has a Hermitian vector bundle on it. We're saying that any complex vector bundle, you're going to be able to construct a Hermitian metric on it. So we're going to prove it by talking about this construction process. So I am a little bit kind of wary of construction proofs now because of the fact that lecture 4 took 3 different sessions to finish, mostly because of that proof that I probably shouldn't have gone into that much detail about. So we're just going to look over the broad strokes of this proof. It's much shorter than the other proof. It's not 3 pages long, but still, we're just going to think about the idea behind this proof, and I'll leave the details to the lecture notes. So first, the statement: if we have a complex vector bundle em pi, then we're guaranteed to have a complex. So if this, then there is a complex sesquilinear positive definite. Oh, I forgot to say that the Hermitian metric is positive definite, right? I was thinking about it and then I forgot. But yes, the Hermitian metric has to be positive definite as well in order for when we were saying that like we're going to inherit or induce the Riemannian metric for from the Hermitian metric, it wouldn't have worked if it wasn't positive definite. So yeah, it also has to be positive definite. So function h h will be an element uh, or h will be a map of the form this. We're going to use the traditional form of it. So yeah, so then there exists this map on it, right? So what does the proof for this look like? So we're just going to sketch the proof. Sketch. So step one is to define it locally. Local definition. So the local definition hinges on the fact that we have phi alpha that goes from pi inverse u alpha to the local trivialization u alpha cross c m. So in fact, this should be CQ. Sorry, this is a typo. So the local trivializations are kind of like I keep saying this there, but this is very important. The local trivializations are like the analog of the homomorphisms to, right. So like for a normal manifold, phi alpha is like u alpha to c m, right? So this is what this is doing, right? This is this is whatever the analog of a local neighborhood is for the vector bundle, and this is whatever the space that we want it to be homeomorphic to is for the vector bundle. But that's called a local trivialization. Local trivialization. I only recently realized why it's called a local trivialization, because this is the local. It's a section of the trivial bundle. The trivial bundle is the bundle that looks like M cross CQ. And if you restrict that to U alpha, then you get this. That's why it's called a local trivialization. So me still discovering new things about older topics that we've already discussed. So the way we define it is we say H alpha at P is equal to of VP WP is equal to, we're going to call this another function so that we don't have to keep writing this, VP WP, which is equal to the sum of VJ P WJ P bar VP WP element of CQ, sorry, CQ. So this is how we define the metric, and on our local trivialization. So the way you can think about that is that we have one local chart on our open cover of the manifold, and we know that again we know that we have an open cover. We've been through this a few times. We know that we have an open cover because it's a manifold. Manifolds have to have open covers. So we know that u alpha exists, and so this is going to give us that. The reason for this format of definition is because it makes it linear in the first input and conjugate linear in the second input. So it gives us that sesquilinear form, right? So so what we're going to do now is we're going to patch together all of the local sections into a global solution, right? And there are going to be no obstructions this time. We're going to be able to do it. So global construction, and we're going to use something we used before in lecture 7 on orientations. We're going to use partitions of unity. So since it's been a little while, let me retrace like what a partition of unity is. So if we have um, a bunch of, let's say we have, I'm going to talk about it in the context of manifolds. So let's say we have, this is like a window into a part of our manifold. So let's say that we're looking at this point P, and there are a bunch of open sets over it, right, from our open cover, U alpha, U beta, U gamma, U delta, etc. So what we were doing in lecture 7 was we were um, weighting in terms of WEIGHT. We are weighting each of these, the contributions to the integral. Remember, like we were using partitions of unity to define the integral, and we were saying that there's going to be a contribution from each of the open sets, but in order to be independent of which open cover that we use to define the integral, what we're going to do is we're going to weight the different open sets that are overlapping on P in order to get the contribution to P, so that the overall weight, so this is the partition of unity, is equal to 1 over all the indices. And this normalizes the value so that the integral is independent of how many open sets you had overlapping over it, as long as the same partition of unity is being used. And right, and so in this case, we're going to be doing a similar thing. We're going to be using the partitions of unity because we defined our H alpha, right, is defined on each U alpha cross CQ, right? And so if we want to add a contribution from each of the H alphas to our overall global H, right, we need to sum it over rho alpha P into H alpha P. Sorry, this would be HP, and this would be H alpha P. And obviously we would have some inputs, VP, WP. We would transfer them over here, and that's how we would define it. And then so this is the global definition. So here, this is the point-wise definition, and then we turn that into a tensor field by requiring that this be smooth. So we then define we define it to be smooth, and so number 3 is just verify the properties. Verify properties. So number 1, smoothness. Smoothness is pretty simple. We assume that the partition of unity is smoothly assigned. So this is a smooth map. There's a theorem. Maybe I will link it in the lecture notes. There's a theorem that says that a smooth partition of unity is available over any open cover of a manifold. So of a differentiable manifold. So smoothness. So H alpha P is defined to be smooth. It's defined to be a smooth assignment. So their composition is then a smooth assignment as well. So number 2, sesquilinearity is we also prove that it's sesquilinear. So for that we have to prove that you basically just have to prove HP VP WP is equal to HP WP VP bar, because we already know it's a linear in the first input. So we just have to prove this, and then let me just write the third one over here. Let's not waste space on the next page. Then you have to prove that it's positive definite. That one's interesting because what you end up with is that HP VP VP is equal to some rho alpha sum over alpha rho alpha of P into VP mod square. Now if VP is not 0, then this is not 0. right? This is not 0. This is a positive number. This is either 0 or a positive number, and since it's not 0, if VP is not 0, therefore it has to be positive. And the argument about rho is interesting. We know that the sum of rho alphas has to be 1, right? So even if some of the rho alphas are 0, they can't all be 0. If they were all 0, then this would not be true. This implies that there exists alpha such that rho alpha is greater than 0, right? Rho alpha of p is greater than 0. So we know that this is at least positive for some of the values in this sum. So we know that this is greater than 0. So therefore, HP is positive definite. So since we've verified these three, right, this is a proof sketch. We haven't gone into detail and proved everything, but I hope you get the idea that there were these 3 steps that we did. We defined it locally, define locally. That was H alpha P, where alpha told us which local chart we were looking at. Then we stitched them together. Using our partitions of unity, rho alpha. And then lastly, we verified that what we got as a result was actually a Hermitian metric. Hermitian metric. So what did we do? We started with a complex vector bundle, and then we construct using nothing but the stuff that we're given on a complex vector bundle. We constructed a Hermitian metric, which means that every complex vector bundle admits a Hermitian metric. So that is proved. Now you would actually have to go in and check all of these things and make sure that the calculations work out in each of these steps, but that's essentially how we're going to do it. And the next proof is actually very similar. So, but before we get to the next proof, we're going to have to define something else. So far, we've made sure that the Riemannian metric is compatible with the complex structure, and that gave rise to the Hermitian metric. So now we need to make sure that the connection on the vector bundle is compatible with the Hermitian metric. So, and therefore be compatible with both the Riemannian metric and the complex structure. So now we're going to define a kind of connection called the Hermitian connection. This is what I was saying. Everything today is called Hermitian. Hermitian connection. And the way that a Hermitian connection is usually defined is that nabla of h of st, right? So this is our sesquilinear form, is equal to h of nabla of s comma t plus h of s comma nabla of t. And this seems a little strange. Like, why is this the compatibility condition? And in order to understand why this is the compatibility condition, we have to remember that h is a sesquilinear form, so it is weird. And if we rewrite this in terms of h hat, then it becomes much more easily understandable. So let's try to rewrite both sides of this equation in terms of h hat. So h st is equal to nabla of h hat of s tensor t bar, right? That's the equivalence between the two. So I've just replaced it with whatever it was equivalent to. And so the other side becomes h of nabla h hat of nabla of s times t bar plus h hat of s times nabla of t bar, where nabla of t bar is equal to nabla of t bar. So now we know that h hat is linear, so we can put those two things together. In fact, let me not waste some space here. Let us just erase that. So we can put all of it into the parenthesis. And so this is actually the Leibniz rule. And so h hat, this is actually h hat of nabla of st. Sorry, s t bar. But look at what we have. We have just this, but the other way around. So actually what this condition is saying is this. Nabla of h bar of s after t bar, or s times t bar, is equal to h hat of nabla of s times t bar, which is exactly what we expected from a connection being compatible with our Hermitian metric, right? So what we're saying is that nabla and h hat commute, which is equivalent to saying that nabla and h commute. But it's harder to see from the h's point of view because h is a sesquilinear form and they've kind of hidden it behind some manipulation. So this is essentially it. This is called Hermitian, or I'm going to call it Hermitian compatibility. Hermitian compatibility. So our second theorem is that every Hermitian vector bundle, we just define what a Hermitian vector bundle is. It's one that has a Hermitian metric, admits a Hermitian connection. It's the same structure of proof. We just need to show that if we have a Hermitian vector bundle, E, M, pi, H, then we will, by necessity, have the Hermitian condition. H of nabla st plus H of S nabla of t. So I'm not going to go over the proof in detail here because it's the same principle as the other one. First, we do a local construction. We then have to prove that we have to do this for the previous one as well. I didn't emphasize that as much, but we did prove it. We looked at whether the form that we had made was actually going to be sesquilinear or not. But we have to prove that our local construction is actually a connection, or actually a Hermitian connection. We then use, we do exactly the same thing. We use partitions of unity to patch them up. And then lastly, we check whether the global function, the global nabla, is actually firstly a connection. So we check whether or not it's linear and it satisfies the Leibniz rule. linear, Leibniz, and then we check uh, if it's Hermitian, which means we check whether this is true. So if I call that 1, then we check 1. And that's how the proof goes. It's very similar. I'll just give an idea of how we define the local version. We need a local frame field, but once we have a local frame field, we basically define it like this. Nabla alpha of E alpha is equal to 0. And this results in a valid connection. This is telling you that the change in the local coordinates is 0 at every point. So you use this, then you promote it using the partitions of unity, and you get something. You get an overall connection. So there are some interesting tricks that we use in this proof, but alas, it would take way too long to explain all of them. So we are going to move on. Hopefully, the overall idea of how we would prove it is apparent, and especially based on how we did the last one. And if it's not, I mean, obviously you can look at the lecture notes. But we're going to move on now. We have one last result to look at, and this is going to be kind of the crown jewel of lecture 10. It's going to be proving that, okay, so first of all, Chern connections. So let's define a Chern connection. So Chern connection nabla is a special Hermitian connection such that on a holomorphic vector bundle. So there are lots of different kinds of vector bundles at this point, so I just wanted to clarify, not a Hermitian vector bundle, a holomorphic vector bundle. On a holomorphic vector bundle, it decomposes as nabla is equal to nabla 1, 0 plus nabla 0, 1. Obviously, if it wasn't a holomorphic vector bundle, we couldn't do this decomposition, so that's why it needed to be 1. And in that case, nabla 0, 1 is equal to bar partial E, the canonical Dolbeau operator. By the way, the canonical Dolbeau operator looks special, but it's actually just the Dolbeau operator on the vector bundle. Like, we're calling it bar partial E to emphasize the fact that it's the Dolbeau operator on the vector bundle as opposed to on the tangent spaces we defined before. But when we go to the coordinate system of the vector bundle, it just is the bar partial operator there. It's not a special operator. So, but it's the preferred one for the vector bundle. That's why it gets the subscript E attached to it. So Chern connections are going to become really important because they're going to be the connection that we add onto a Kähler manifold, and in the light of this manifold, we get a special decomposition of F nabla. F nabla. So F nabla is a 2 form, right? Because F nabla is equal to d omega minus omega wedge omega, and omega is a 1 form. So f nabla is a 2 form. But in the complex sense, a 2 form can either be a 2-0 form, a 1-1 form, or a 0-2 form. And in general, a 2 form can have components of all three of these. But when your connection is the Chern connection, um, a special thing happens where the 2-0 form and the 0-2 form parts both cut out, and you get just a 1-1 form. This is going to become important in the next lecture when we're going to talk about Kähler manifolds, what this 1-1 form is going to be. And so we should prove this theorem. The curvature induced by the Chern connection is a 1-1 form. So we're going to actually prove this one, and hopefully it won't take too long. But this one is one that is important to pay attention to. So firstly, we're going to decompose the connection. We're going to say nabla is equal to nabla 1, 0 plus nabla 0, 1. This is essentially the same thing as doing d is equal to partial plus partial bar. It's the same type of decomposition. We just make sure that each of the sub operators in the sum are operating on different parts of the input and produce or are producing different parts of the output. Okay, so yeah, so we know that because we have the Chern connection, since it's a Hermitian connection, it satisfies the Hermitian condition, and also because of its own definition, we know that nabla 0, 1 is equal to the canonical Dolbeault operator. So it's also compatible with, not only is it compatible with the Hermitian metric because it's a Hermitian connection, it's also compatible with the holomorphic structure. This is what we want, right? We want our connection to be compatible. We want all of our we want all of our structures to be compatible with each other so that we can have a manifold that has all of them. That is kind of what we've been building up to. And if I haven't said that already, it's maybe because I haven't crystallized that idea yet, but that is essentially why we are looking at all these compatibility conditions. So eventually, we're going to have one manifold that has all of them. And if they're not compatible, one of the structures is going to break the other structure. So we don't want that. Okay, so step 2. Step 2 is we decompose the curvature. So far, we've said that f nabla is this whole nabla x, nabla y, dot, 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 right? But there's a decomposition of f nabla as nabla after nabla. And this depends on something called the exterior covariant derivative. The reason for this decomposition is going to be eluding us for a little bit, but hopefully I'll be able to add it back into the notes afterwards. But we're going to use this in order to decompose our curvature tensor. So basically, we're going to put in two different instances of this. So nabla, let's go to the next. That means that f nabla is going to be equal to nabla 1, 0 plus nabla 0, 1 times nabla 1, 0 plus nabla 0, 1. And so we're going to get a bunch of terms. One of them is going to look like this. So we have this nabla 1, 0 and nabla 1, 0. So each of these is a map that takes us from omega pq to omega p plus 1 q, right? So if that's the case, and if f nabla is a 2 form, right, its overall grade is 2, then this must be the part that takes us to a 2-0 form. We're going to have to prove that this 2-0 form is equal to 0. There's going to be another part that is nabla 0, 1 after nabla 0, 1, and this is going to be the 0-2 form for similar reasons. And so this part, we can already tell that this is 0 because we know that this is equal to bar partial E, like the canonical Dolbeau operator, and we know that the canonical Dolbeau operator squared has to be equal to 0. That's from our results in Dolbeau cohomology. So, so this part is already has to equal 0. But it only equals 0 because we're on a Chern connection, because we did, like, the fact that this is equal to this, right? The fact that this is equal to this is only true if we have a Chern connection. So that's how we're using the Chern connection to say that this is 0. So there's one last part, which is this term that's multiplied with this term, and this term when it's multiplied with that term. Those are the mixed terms. And so I'm just going to write that out once. Nabla 1, 0 after nabla 0, 1. These are going to both give, and in the other order as well, these are both going to give, this one is going to do increase the p by 1, p plus 1, and this one is going to increase q by 1. So these are going to be the 1, 1 parts. We don't have to do anything about these. These are the parts that are going to remain after, when the proof is over. So right now, the only part that remains to be proven is that this 2-0 form is 0. So that's what we're going to do next. So we have to prove that this is 0. So how do we do that? The way we do this is, firstly, we expand in a local frame field. So let's add a local frame field, alpha equals 1 to m. Then we know that we can decompose the connection into a bunch of connection forms, omega alpha beta tensor E beta. We know that F nabla is equal to d omega minus omega wedge omega. But we know that d can be decomposed into partial and partial bar. So this is actually equal to partial omega plus partial bar omega. Why did I do it like that? What I was trying to do is partial plus partial bar omega minus omega wedge omega. And that is equal to partial of omega plus partial bar of omega minus omega wedge omega. And so if we think about right now, this is where it becomes important that omega is a 1-0 form, right? So because we're on a specific kind of manifold or a specific kind of local frame field, we have that this is right. This is the canonical Dolbeau operator, and we have that the frame is holomorphic. So therefore, omega is a 1-0 form. It's 0-1 part will, like, overall it's a 1 form, so it can have a 1-0 part and it can have a 0-1 part. Its 0-1 part is equal to 0 because we're on a holomorphic frame, and the 0-1 part of the covariant derivative is, or the 0-1 part of the connection is the Dolbeau operator. So we established that last time. That means that that part had to go to 0. So um, now that we know that omega is a 1-0 form, we can now deduce what kind of forms these are. So if this is 1-0 and this increases the first form by 1, so then this is the 2-0 form. This is the 2-0 form, because the uh, Dolbeau operator will increase the p grade by 1, right? Or the holomorphic grade by 1. And so then this will be is a 1-1, because this is 1-0 and this is increasing the anti-holomorphic grade by 1. We now know that this is a 1-0 form, right? So this does change. 1-0, 1-0, therefore its wedge product is now, this is now a 2-0 form. So what we really want, okay, so what we want is the 2-0 part. So the 2-0 part is, let's say, omega 2-0, or f nabla 2-0 is equal to partial omega plus or minus omega wedge omega. So now there's a sub proposition that I think I'm just going to skip, and we're going to use the result. But it's in the notes. Partial h is actually equal to omega h, given that we have the Hermitian condition. Hermitian condition. So you can use the Hermitian condition to prove this. That was that h of s t bar nabla equals dot dot dot, that one. So you can use this to prove that I put an arrow towards given. You can use that to prove this result. You can also prove that partial bar of h is equal to h omega minus h omega transpose. This one won't be as useful for us, but this is the one we're going to use. Since this is true, yeah, so you just expand in terms of omega, like wherever you see nabla of some field, you expand that in terms of, like, instead of s we use e alpha, and instead of t we use e beta, and we just like expand it out. We use the fact that h hat of e alpha, in fact we don't use the tensor form, I think we just use the normal form, h of st. So we use the fact that this is equal to h alpha beta bar, and we just kind of expand it out, and then we do the matrix multiply. And if you do the matrix multiply correctly, then you get this result, where these are all matrices. H is a, oh, I haven't maybe defined what H is. H is just this. In this proof, there wasn't, this is another did not have enough time to cook thing of this proof, is that there's some places where I refer to it as capital H and some places where I refer to it as small h. So, right, but H is the matrix, and H is component. You can think of H as being the matrix and H's components to be H alpha beta bar. So, yeah, so H is a matrix where, yeah, like that. So, right, so what do we do with that? What we do is that, first of all, we note that partial square of H is equal to 0, because this is identically 0. And then we evaluate partial square of H. So partial of H is this, right? So partial square of H is partial of H, which is equal to partial of omega H. And then you have to use Leibniz rule. So we get partial H wedge omega plus H into, I think you have to do a wedge here too, I'm not sure. Partial of omega. Oh, well, you don't, right? It's the same reason you didn't have to the last time, because H is not a form yet. H is a function. So we can just write it like this. So I am to a certain extent sight reading this. So then that means that partial h, we're again using this here, and so we're saying this is equal to this, which means that we move the function to the other side, so then we get this, and then this is exactly what we were after, right? We said that this is equal to that. Oh, we're gonna need we're going to get an extra minus sign because we're in order to flip these. So we're gonna get minus h omega. So then we get this, or equivalently, we get partial omega minus omega wedge omega. And that is exactly what we have here. So since h is invertible, it can't be degenerate. So therefore, this has to be 0. So here we remember we said this, right? So this was equal to partial bar square h is equal to that, which means that partial bar square h into this whole thing, partial of omega minus omega wedge omega, is equal to 0. So we're doing the same thing that we do with quadratic equations, like solving quadratic equations. We're saying that one of the factors has to be 0 in order for it to be equal to 0. So since this cannot be, its determinant cannot be 0, therefore this must be 0. So, but that's equal to f nabla to 0, right? So therefore, that implies that f nabla to 0 is equal to 0. So the 2, 0 component is 0, and we already showed that the 0, 2 component is 0. Therefore, f nabla has to be a 1, 1 form. And that concludes the proof. We did skip over a little bit. We skipped over the proof of this statement. I don't think it's that necessary to understanding the overall thing, and I think in the lecture it's more important that I cover how to understand the proof rather than how to prove every single step. But that's overall it. Let's kind of summarize what we did so far in this proof. And now it's over. We've just proved it. So what we did was we said nabla is equal to nabla 1, 0 plus nabla 0, 1. And then we decomposed f nabla into 2 of these, right? I'm not going to write it out all again, but we did that. Then we FOILed it, we multiplied it out, and then we saw that there were various operators. And so, for example, the 1, 0 after the 1, 0, that would give us the 2, 0 part of f nabla, because overall f nabla is a 2 form, right? So if one of its parts looks like this, then and it overall increases the p grade by 2, then that must be the 2, 0 part of it. So, and then the same thing that we did for the other ones, and then we said that this part was 0 because it was equal to the bar partial operator and bar partial square operator, which is equal to 0, right? So and then the last part gave us the 1, 1 form, and we didn't have to touch that because we're not saying anything about the 1, 1 part. So then we had to figure out whether the 2, 0 part was 0, and then we ended up showing that f nabla was 2, 0 is equal to partial omega minus omega wedge omega, and then we showed that there like we eventually ended up with this equation and that was equal to 0 because partial bar square of h is equal to 0. And in order to get from here to there, we used this equation, partial of h is equal to omega h, and so then we use the standard like quadratic equation solving technique, which is we said that one of the factors has to be 0. It's not going to be this one, so therefore it has to be this one. So therefore this is equal to 0, but this is the same thing as this, so therefore that implied that f nabla 2 0 is equal to 0, which means that f nabla and we already showed that f nabla 0 2 is equal to 0, so therefore f nabla is an element of omega 1 1, and that was the big result. This is the theorem. That was the proof overall. So that concludes our look into Riemannian manifolds. We've looked at all of the structures that we need in order to start talking about Kähler manifolds, especially the Kähler form. So next time we're going to look at that. So a recap of what we did today. We looked at Riemannian metrics, and Riemannian manifolds. We looked at the Levi-Civita connection that was given to us by the fundamental theorem of Riemannian manifolds, a very important sounding name. Levi-Civita connection, and this was a metric compatible and metric compatible plus torsion free. And we also looked at lengths and angles. I keep wanting to spell lengths as L-E-N-G-H instead of L-E-N-G-T-H. Lengths and angles. And so then once we define the Levi-Civita connection, we defined Hermitian metrics. We also looked at H versus H hat. We looked at Hermitian manifolds, which are manifolds that have Hermitian metrics. We looked at Hermitian vector bundles, which are vector bundles that admit Hermitian metrics. Then we looked at we proved, well, we sketched the proof of every complex, I'll shorten, complex vector bundle admits a Hermitian metric. We looked at the Hermitian connection, which is a connection that is compatible with the metric, the Hermitian metric. And then we proved that the every Hermitian vector bundle has a Hermitian connection. And then lastly, we looked at the big theorem, or we defined Chern connections, and we had this big theorem that F nabla is a 1-1 form if nabla is Chern. So that's what we did so far. Next time, we're going to have the big lecture, the big reveal of the Kähler manifold. Kähler manifold. So that's going to be lecture 11. And then from then on, lecture 12 is going to be Haji decomposition on Kähler manifolds. And then lecture 13 is going to be um, a specific kind of Kähler manifold called Calabi-Yau. So the rest of the lecture series is going to be about Kähler manifolds, which I kept as like the North Star of this lecture series, so that we could kind of have a oriented goal to get to. So see you next time when we're going to talk about Kähler manifolds.